morning everyone, and welcome back to our day 2 of our workshop, and good to see you again. I know, as we discussed earlier, after yesterday dinner on the board and managing to come early around 9 a.m.
Someone's still on the boat, maybe.
Yeah, you never know. I said, how many of you felt like moving the boat fast after a couple of glasses of wine? Nobody? Nobody like me? Okay. Anyway, so yesterday actually we spent our time looking at AI for security, and we discussed how we can use AI for security problems, and it was great to see actually the energy the audience brought to the session. A lot of questions. I really like to see it. The energy you brought to the session, and hopefully more people will arrive later, and I hope we will continue the same dynamic today as well. Today actually we are going to turn the focus around to look at the security of AI itself, diving into the challenges of securing AI system, and of course exploring the topic of large language model security. We will look at the program. In the morning we will look at security of AI. In the afternoon we are going to look at LLM security and the application of LLM for security problems. This is also very important because AI can help to tackle some security problems, and also at AI itself brings some challenges to the security domain. So that's why looking at security of AI itself also very important. As I mentioned earlier, just a quick reminder before we begin, the lunch menu would be different than the yesterday, because yesterday we had lunch in the main hall. Today, if you look at the workshop schedule on the website, you will find the exact location. Even I don't know where it is, but I know it's different. You can find everything as conference organizers. Always inform us, look at the website. So if you look at the website, you will find exact menu detail. But I know for sure it is different from yesterday. With that, I think we can start. So it's my pleasure to introduce our first speaker. Who will okay, you're going to start first. No, this is the second. Yeah, Samuel. So Samuel is going to speak on scalable generation of invariance-based adversarial examples using SECAI. Samuel, is over to you. Yeah. So as usual, guys, you get 25 minutes for long papers, and please make sure to stop by 20 minutes, leaving some time for Q&A, because we spend a lot of time and money to come here, and then it's good to have a kind of discussion around your work. So then please leave at least 5 minutes for Q&A. Please, when you're ready, go ahead.
Introduction. Good morning to the people here. So in the next couple of minutes, I'm going to talk a little bit about invariance-based adversarial examples, and especially in computer vision, and how we created a pipeline to automatically generate those invariance-based adversarial examples. This is a joint work done with Nocker, who is also here in the audience, Florian, Merkle, Pascal, Schöttle, and myself, Oberhofer. So, as we all know, machine learning vision systems are now embedded in cars, they're embedded in financial platforms, and even in medicine nowadays. So, while their accuracy is impressive, their security matters even more, so it's crucial to study those models also adversarially. And to illustrate this, I brought this example, which is also quite famous, Here on the right, you can see a stop sign where researchers have like strategically placed some stickers such that automatic street sign recognition system does not recognize this as a stop sign anymore, but rather it sees it as a speed limit of 70 kilometers an hour, which of course could lead an autonomously driving vehicle to drive straight through an intersection, which of course would be enormously dangerous. In general, adversarial examples are just images which are classified differently between humans and machines, and it's just images that fool a model, and that's why understanding them is just crucial for being robust computer vision systems. Today I focus on a little bit less explored flavor of these adversarial attacks. And next we'll look into what exactly those are. So traditionally, researchers have studied so-called sensitivity-based adversarial examples, or perturbation-based, or SBAEs for short, where you can put imperceptible dusting of pixels onto the image, which then flips machine learning classifier's prediction, while humans still recognize the original object. This reveals that models can be fooled by like small and carefully crafted perturbations that don't really affect human perception at all. In this example, we can see a benign image of a cat on the left, which is classified by an image classifier as a cat with 89% confidence, let's say, and then we can add some small perturbations to the image. Here, of course, it's not even closely visible on a projector, but even in the raw JPEG you wouldn't be really able to see this noise, and this then flips the classifier's prediction to the class guacamole with an even higher accuracy or confidence of 97%. In contrast, in so-called invariance-based adversarial examples, these are the ones that we investigate, they basically look at the flip side of things. So you try to make sizable and visible changes to images so that humans detect a new object, so they classify it as something differently, and yet the model kind of stubbornly sticks to its old label. In this image, for example, we can see this is the benign image of a bird, and then researchers have put this image of a pineapple on top of the bird, occluding the bird almost completely, so that we could assume that most people would classify this image as a pineapple and not as a bird, yet the model, as I said, stubbornly sticks to its old prediction of the bird. They're called invariance-based because they exploit the excessive invariance of machine learning classifiers. So you can change the semantics of an image quite a lot and still have the classifier stick to its old prediction, as I said. In general, both flavors of these adversarial examples highlight basic misalignment between human and machine perception, and wherever there's such a misalignment, there's of course room for nefarious actions that can be done. And yeah, basically in simple terms, any adversarial example is just an image which is consistently classified differently between humans and machines. Creating these invariance-based adversarial examples has historically been quite difficult or tedious and very often involved manual processes. Previous work relied on kind of painstaking manual pixel edits in the images. For example, here we see a handwritten digit 8 from the famous MNIST dataset, and researchers can then manually edit pixel in this image, which then are still classified as the number 8 by a machine learning classifier, but maybe looks way more like the number 9 for us. So if you, for example, take these kinds of pixels and make them more black, it can happen that the machine learning classifier still predicts it as an 8, but most people would detect it as a number 9. For more complex images, we first need to identify the most important regions of an image first. Like in the example we saw before, I need to identify where the pineapple or where the bird is so that I know where I can do the changes on the image. And this can be done by conducting an eye tracking experiment, where we look at gaze data from humans to identify which regions are most looked at by humans when classifying these images. And consequently, we lacked a really practical way to study large number of images, of real-world images, because we had to do human subject experiments to gather this eye gazing data. And our goal was to eliminate these bottlenecks with an automated pipeline. This is mainly our goal. As I just mentioned, the eye tracking studies are conducted in order to identify the important regions of such an image, and in our approach, we substitute human eye gazing data with importance maps that we generate using techniques from the field of explainable artificial intelligence. These algorithms, they assign a so-called importance value to each pixel in the image, and they look at the inner workings of the neural network and how the neural network activates when making its decision to decide which pixels are relevant and which are not as relevant. This then gives us a heat map, like here on the right, where the red pixels signal important parts of the image, and the blue pixels identify regions that were not really looked at by the neural network when it was making a decision that this image should be classified as a fish, basically. In our work, we contribute a scalable algorithm for generating such invariance-based adversarial examples. We use XAI techniques to avoid the need for eye-gazing data from humans, and our approach is agnostic to the specific XAI algorithm used. We just need some kind of importance map. It's also agnostic to the machine learning model used to classify the image, although the results themselves might vary a little bit. It works with every machine learning classifier that you use. And additionally, we validate the images that we are able to generate with the human subject study that we did with 166 participants. Now, let me give you a brief overview of the algorithm. So first, we start with the so-called base image, which we want to manipulate. In this case, it's this image of a church. We can then use XAI. In our case, it's an algorithm called integrated gradients, which we use to compute such an importance map. And next, we compute a binary mask of the most important pixel data using a small threshold value. And then we can apply this binary mask to the original image. This gives us then an image where the most important parts are occluded or are cut out, and only the less relevant parts remain. We can then perform the same operations on a second image. This is then our attack image, which we want to insert into the base image. In this case, this is an image of a dog, and we perform the same operation. So we first compute the importance map, then we can use this importance map to use the same threshold to mask it out. And also we compute the center of mass of this mask, which is indicated by the yellow, by the orange circle here. And we use this center of mass so we know how we need to shift the attack image in an X and Y way to insert it in the right spot of the base image. So this is what we use there. And then we insert it there. This then gives us our combined image, which looks like this. This is an invariance-based adversarial example candidate like this. And basically what we do is we perform these operations that I just outlined for bigger and bigger masks. And then at some points the mask gets so big that the classifier flips its prediction, for example, away from one class to the other, from the base class to the attack class. And once this happens, we go back one step, so we make the masks a little bit smaller again. And this gives us the image with the maximum amount of attack image that we were able to insert while still leaving the label of the base class. This then is our final invariance-based adversarial example candidate. We call this a candidate specifically as if you recall, it's only a real adversarial examples if humans and machines classify differently, and at this point we simply do not know that yet. So maybe let's look at how our experiment was set up. We used the ImageNet dataset. This is a subset of the bigger ImageNet dataset, which only contains 10 classes, and easily distinguishable classes. And we use the validation set of this dataset, which has approximately 4,000 images. This provides us a very clean dataset and a quite realistic benchmark because they're rather diverse real-world images. Our model that we used was a mobile net V3, which was pre-trained on ImageNet, and integrated gradients, as I mentioned, was the primary explanation method that we used, although we looked at others and verified that they behave quite similarly in our experiments. This pipeline then generated 1,924 such invariance-based adversarial examples, which successfully covers 98% of all base and attack images. We did not see meaning or significant differences in how much of the attack image we were able to insert before the classifier flipped its prediction, which is a number we call alpha, and the specific class of base or attack image. So there wasn't a significant difference in how much we were able to insert depending on the specific class. So on the right-hand side here, we can see one of our 1,924 images. This is an IVAE candidate with base class dog and attack class golf ball. This means we inserted the most important regions from the class, from the golf ball image into the areas of highest importance of the dog image. By the nature of the generation algorithm that we use, the machine learning classifier still predicts this image as a dog. And for this image to be a successful IVAE, the majority of humans would need to classify this as a golf ball, or basically as anything other than a dog would suffice for some definition. Next, let's briefly look at the setup of our human subject experiment. To test how people actually perceive these images, we ran a remote survey with 166 participants, ranging from 18 to 66 years old. And each participant saw 100 images for 1 second each, and then, which forces a gut level response, an immediate response, and then they chose 1 out of 4 available options. This design reduces random guessing and measures the immediate perception of humans. We deem an image successful if more than half of participants chose a label different from the base class, as I said, and under this definition, 49 of the tested images were successful. We saw that the success differed from class to class, so there were significant differences. On the easy end, we saw that 32 participants chose the base label for the chainsaw class, whereas on the other end, on the difficult end, 81% of people chose the base label for the golf ball, if the image had base label golf ball. In this plot here, we can see the success rate of our generated IVAEs grouped by the label of the base image. So the higher the base label rate here on the y-axis, the more often humans actually agree with machine classification. So this means we want this number to be as low as possible in this case. Chainsaw having a base label rate of 32% means that more than 2/3 of participants were fooled by the IVAEs where we inserted pixels into an image of a chainsaw. One common feedback that we got from participants was that they found golf balls to be really easily distinguishable and detectable, and our hypothesis on that is that this might have to do with their very distinct dimples and them looking the same from each angle you might look at golf balls. So this is also reflected in the number of successful invariance-based adversarial examples that we were able to generate for the class golf ball, as you can see here. which also shows that there are categories which are just easier for humans to correctly identify compared to others. Nevertheless, we were able to generate successful invariance-based adversarial examples for each class in the data set. Recall that an invariance-based adversarial example is defined as successful if the majority of humans misclassify it. Given this definition, as I said, 49 out of our 100 tested examples were successful. We then looked at those examples that were successful and tried to gain some insight on what made them more successful. First, in most of them, the final label was the attack label. Now, what is the final label? Remember that we stopped increasing the size of the mask once the machine learning classifier flips its prediction to a different label. This new prediction does not necessarily need to be the attack label. We saw that sometimes the ML classifier switched to a whole other label completely. In our study, though, we saw that invariance-based adversarial examples are, or the successful ones, often are images where the model's final label was indeed the label of the attack image. Another insight, which might seem trivial at first, is that the more of the attack image we were able to insert, the more likely the resulting IBA be a successful one. If we think back to our image of the dog and the church, if we can replace almost the whole image, church image, with pixels from the dog, it becomes extremely likely that a human will not be able to identify the original class, which the neural network, of course, by definition still predicts. Finally, we conducted another round of image generation where we incorporated these two findings from the human subject experiment. Specifically, we only want images where we were able to substitute more than 80% while leaving the classifier's prediction unchanged. This is what high alpha means in this case. Alpha again tells us how much of the image we are able to replace before the prediction flips. And additionally, we filter for IBAE candidates where the final label matches the attack label. This gave us 114 high-quality IBAEs. These here are three rather extreme examples where only very, very little of the base image is left. If you look at the leftmost image, you can see the blue shape over here, which is left over from the base image, which was depicting a parachute. The machine learning classifier still classifies this image as a parachute, whereas most human beings will give the class garbage truck here. Similarly, in the middle, we see an image which almost exclusively consists of pixels from the church image, while MobileNet classifies this as a class bound. And then, let's see. Exactly. So, finally, let's look at the conclusion. So finally, to conclude all of this, we presented a scalable and SECAI-based method for generating these invariance-based adversarial examples on quite complex data sets. We conducted a human study which confirmed that human deception is possible, and it increases with the amount that we are able to insert, which highlights, of course, the security risks there is. And we released this data set of high-quality IBAEs for further research, and we demonstrate the feasibility of generating such examples, which can also resemble natural images that really fool humans. And for the limitations, we only looked at one XAI method in depth, and we have also only looked at one machine learning classifier, where of course a more broad study could gather additional insights in how generalizable these invariance-based adversarial examples are. For future work, we think about conducting a further human study on these high-quality invariance-based adversarial examples to further check if they really do work as well as we think they should. And also, as I said, explore alternative models for classifications, more modern approaches like vision transformers or multimodal LLMs. So, in summary, to put all of this together in one sentence, we saw that invariance-based adversarial examples can really fool human perception, and we showed that it's really possible to generate them at a large scale. And with that, I conclude, and I'm happy to answer some questions.
That's brilliant. Thank you. open the floor for questions.
Thanks, you asked.
We have time for 2 questions.
Thank you for the interesting talk. Is it possible to perform these attacks in the real world with the normal adversarial attacks, printed stickers?
With the printed stickers, well, I mean, we looked at image classifiers that take these images. So you would mean like generate such examples and then based on that produce stickers that you would put on real world? Was that the question? I would assume that it's quite possible. It really depends on how generalizable and robust these invariance-based adversarial examples are. So if they turn out to be quite robust, then I would assume that also in the real world they should work. There, of course, you have difficulties like different angles, different lighting, and then if these examples are not as robust, but we suppose that they should be quite robust, if crafted in a robust way, then I think they should work. It also depends if you try to go to the extreme, so make the resulting patches that are still left as small as possible. The invariance-based adversarial example might be not as robust, but it might be more effective, so I guess there's a little bit of a trade-off there. But in principle, there shouldn't be anything preventing it from working in the real world.
Any other questions?
Yeah, I think I'm loud enough.
Yeah.
Thank you so much. I have a quick question about the user study or human participant experiment. Did you take into account people with visual impairments, such as color blindness, and what kind of effect?
We asked for them, it's also outlined in the paper, we asked for any visual impairments, and we didn't have any color blindness. We had people with visual impairments like short-sightedness and stuff like that, but we only included the data of participants whose vision was corrected to normal at the time of the study. So like they were wearing glasses or whatever. We had 2 or 3 participants which are not included in the results of people that said that they had visual impairments which they did not correct for at the time of the study, so we excluded them from the study.
Thank you. Just a question while I'm working there. So have you talked about any defense mechanism?
Defense mechanism? Yeah. So the next step, of course, also when you have this adversarial example is, or a logical step, would be to use them in training to make models more robust against such attacks, which is shown in literature to work.
Okay.
It's also shown in literature to be a little bit of a trade-off. If I train with sensitivity-based adversarial examples, I might make my model more susceptible to invariance-based adversarial examples and vice versa. And it's still a little bit open research question how exactly we can train models to be robust against various attacks while still not losing accuracy and not getting less robust against other attacks.
Maybe adding the watermark, some code as well. Yeah, again,
it might work. Yeah, nice idea. But yeah, basically putting them in or fine-tuning a model with crafted invariance-based adversarial examples is one way to train them, which also makes it important to have a way of automatically generating those so that we have a large corpus of data which we can train our models to be more robust against.
Thank you very much.
Thank you.
Let's